is Vitor. I'm with the Toyota Research Institute, and in this presentation I'll be talking about one of our latest works entitled 3D Packing for Self-Supervised Monocular Depth Estimation. Monocular depth estimation is the task of going from one single RGB image to a per pixel depth map. This information can then be used to lift 2D information into 3D space, generating vision-based point clouds that can then serve as input to a series of downstream applications. Within monocular depth estimation, there are a series of methods that, instead of relying on ground truth information at training time, focus instead on self-supervised learning. These methods use strong geometric priors to project information from one camera frame into another, and minimize an appearance-based photometric loss. Monocular self-supervised methods go one step beyond and do not even require stereo pair, using instead one single camera and projecting information from subsequent time steps. This training approach is highly scalable since it only requires video information, has a strong objective in the form of geometric priors, and leverages the dense texture signal from every pixel in the image. However, it also has some challenges. One of them is the difficulty in leveraging the fine-grained information containing high-resolution images. Another challenge is scale ambiguity, since the photometric loss is agnostic in respect to scale, which makes the resulting models accurate up to a factor. In this paper, we address both of these challenges and show how it is possible to both leverage high-resolution images to achieve state-of-the-art in self-supervised monocular depth estimation and also generate scale-aware models from a single camera without explicit ground truth depth supervision. Our first contribution is PackNet, a novel architecture for monocular depth estimation that focuses on preserving spatial information between layers. Instead of aggressive downsampling via striding or pulling or upsampling via interpolation, we propose to learn how information can be compressed and decompressed without discarding important spatial cues and fine-grained details that can lead to better depth estimates. This is done using novel packing and unpacking operations that work by folding spatial dimensions into feature channels, so no information is discarded during the downsampling stage. Similarly, during upsampling, we unpack this folded information back into spatial dimensions, so we can recover the original resolution without interpolation artifacts. 3D convolutions are used in both stages, so packed and regular spatial information can be processed at the same level. Because we are not discarding information during any stage of the encoded-decoding process, with packing and unpacking we can recover the original input much more precisely than when using standard downsampling-upsampling techniques. Here is an example of the packing operation. We start by folding the input tensor, so spatial dimensions of a 2x2 grid, in this case, are stacked together as extra feature channels. We then apply 3D convolutions to this folded tensor, producing a series of 3D feature maps that are then also stacked together as extra feature channels. 2D convolutions are then applied to this tensor to generate the final output, with the desired number of channels. The unpacking operation follows the same steps in inverse order. Our second contribution is weak velocity supervision, that proposes to use instantaneous velocity measurements as a way to solve the scale ambiguity problem of the self-supervised photometric objective. We impose a loss on the magnitude of the predicted translation of the pose network, so it approximates the measured velocity between frames. This allows the pose network to gradually converge to a scale-aware model, and this property is also transferred to the depth network to maintain consistency between estimates. We evaluated our proposed PackNet architecture and weak velocity supervision on the standard KITTI benchmark. Our results establish a new state-of-the-art in self-supervised monocular depth estimation that is even comparable to fully supervised methods. We also show better boundary definitions and better resolution for fine-grained details and faraway objects. Additionally, we show that PackNet scales better with number of parameters and higher resolution images relative to the ResNet architecture. We also introduced Dense Depth for Automated Driving, DDAD, a new dataset generated using data from our vehicle fleet. It contains scenes collected in the United States and Japan, obtained using 6 cameras and 4 luminar sensors to produce a 360-degree view at 10 Hz with corresponding ground truth projected depth maps. We use DDAD to show that PackNet also achieves better performance when evaluated considering longer distances, up to 200 meters. In fact, the gap in performance between PackNet and ResNet improves when longer distances are considered. Training and inference code for our models, as well as the DDAD dataset, can be found in the following links. We are also currently hosting a monocular depth estimation challenge for DDAD, so feel free to check that out. If you have any questions, please contact us. Thank you very much.